Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Good afternoon, Mike.
Hey there. It is, in fact, afternoon.
It is summertime, and I have this habit in the summer that I listen to what on the islands they call island music, reggae, dance hall, stuff like that. I don't do it on purpose, but it just seems to happen every summer. I almost feel like a cliche over here. Anyway, a couple weeks ago, I started listening to Keznamdi, and this is a record from a few years ago. It's called Bloodline. It's a reggae dancehall record. It's got some good stuff in it, and I just keep putting it on, and then I just keep feeling like, wow, here I am, cliche Eric again with my island music all summer long. At least it's nice and hot out there.
I assume you mean islands off the coast of Norway.
No, I am thinking of my family members back in Hawaii. They just talk about, you ask them what type of music they listen to, and they say island music. And they mean reggae dance hall. So that's kind of what I thought everybody calls it.
I've been listening to what I listen to during the summer as well. For some reason, when the weather gets hot, I turn to hardcore.
So Mike's island music.
I've been listening a lot to this album called Alone Together by the band Show Me the Body. They've been around for a long time, I guess, 2009 or something like that, but I've never really listened to them. I like this album a lot, though. It came out about a week ago, and it's kind of like a cross between punk and hardcore.
Oh, interesting.
And I know you will probably object to this comparison, but it gives me similar vibes to The Shape of Punk to Come by Refused.
Whoa, that is a huge claim. I'm feeling a little sleepy today. I am not prepared to accept a claim like that. You got to give me some time to prepare myself. You're going to make a claim like that.
Yeah, it's pretty bold.
What does it remind you of that? One of the best records of all time. And Mike, I try not to have the, I was there first, but when they started playing The Shape of Punk to Come on the show The Bear, I was like, what is this? They weren't there. They didn't see these guys play.
They use certain of the songs I've seen it on other TV shows too, where they use it to sort of like convey this sense of anxiety and franticness and tension. But for those of you who don't know us personally, The Shape of Punk to Come by Refused is one of Eric and I's shared mutual favorite albums of all time.
Yeah, I mean, when it came out, everybody I knew at the time was like, wow, this is the greatest thing I've ever heard. It's just, game's over. I did see them play. I did see the singer get up on stage and say, "We are Refused, the all-gay band from Sweden." Because they had traveled across the southern U.S., and one of the members of the band is gay, and some people were heckling them. So then they took on this like they were just pre-heckling the crowd. Come at us.
I wouldn't necessarily, I mean, this album is only a week old, so it's kind of hard to put it into the same pantheon, but it gives me similar vibes in the sense that it's got a little bit of a political flavor to it, and it's a little bit kind of genre bending. If you're a serious hardcore fan, it's probably going to be a little bit too indie rock. This
is piquing my interest. I got to hear it at least. That comparison is very bold.
Yeah, I would give it a shot. It's I realize I've kind of set your expectations pretty high at this
too
point
high. Way too high. Yeah.
But yeah, I think it's a really solid album, and if you give it a few listens, I think you will like it.
I will check it out. It's called Alone Together. Friends, if you'd like to support the show to help us pay for our hosting costs, keep it going, we do have a Patreon. We have a membership level of $4 a month, and we want to thank our Patreon subscribers. Thanks so much for supporting Picture Me Coding. It's hard to do the show without your support, and we appreciate it.
Also, if you use Blue Sky, I know that not a lot of people do, but if you use Blue Sky, please look us up there and subscribe. We could use some more followers. And then I wanted to announce something. In about a month, I'm going to be giving a talk at DataCon LA 2026.
Oh,
Uh, it's
interesting.
on it's on August 22nd
Oh, my
at
friend Justin's
Cal State Long
birthday.
Beach.
Cal State Long Beach.
Will he be
Wait, it's
there?
DataCon LA, but it's in Long Beach. Is Long Beach in LA?
Close enough.
It's a tough question. Yeah. What kind of, how long do you think that conference goes for? Is it a weekend conference or?
No, it's like a 1 day thing, kind of like a weekend thing, like Scale. In
Okay.
fact, I found out about it at Scale. But anyway, I will be giving a presentation there, basically on the topic of using various AI tools to understand query optimizers, which is kind of my
Interesting.
favorite topic at the moment. And I actually have a discount code if anybody would like to sign up. It's
Nice.
MULL25. If you use that code, you get a 25% discount.
Okay,
It's
cool.
actually a pretty inexpensive conference in any case. Looks like some of the talks are going to be pretty interesting. So if you're a Southern Californian, consider it. We can carpool if you want, if you live in San Diego.
And you're not crazy. You can get a 25% discount and see Mike talk at DataCon LA. That's pretty cool, Mike.
At least not crazier than me.
Yeah.
That's the
I've
benchmark.
never given a conference talk, big conference. I've given talks like little meetup stuff back when meetups were a deal. I gave my best meetup talk, I think, was the Monads for Functional Programming one. I did that a couple times based on the Phil Wadler paper. I think that was really good. It was recorded at one point. I was pretty happy with that. I did that at Papers We Love, actually, but I've never done a conference talk. You get stressed out? You get nervous, worried? You see a big audience in front of you?
Not too much. I did the I used to do the Pi Data conferences pretty religiously, and
Mm,
I gave talks at the one in New York and the one in Chicago back in the 20 teens. And I get nervous, but I have sort of a physiological advantage over most people, which is I have a heart rate of about 40. So I
so,
don't uh, I don't really exhibit stress. I feel it, but I don't really exhibit it.
so it ticks up to maybe 42 when you get nervous. I always think if I'm going to give a talk, there's going to be at least one person who stands up at the end and asks something just really like not that interesting, like terrible. People always ask questions at talks that are like, I'm going to ask a question now to talk about how much I know.
Yeah, it's been my experience that no matter how much I study this stuff and prepare for it, the first question is always something that I have absolutely no clue how to answer. So
Oh, yeah.
I just kind of accept that's going to happen.
Often
But
they're good questions, but every time someone stands up to ask a question at a conference as a talk, I have like this skepticism level that goes up like, okay, what are you going to try to demonstrate for us here? um, All right. So, what did you want to do today? You had an idea for today, and I was into it because I am into the past right now because the present and the future are worrying me. The past is so sunny and happy all the time, Mike.
so I've been an ACM member for many years now, probably going on 20 years.
Hmm.
ACM is the Association for Computing Machinery.
I was a
Uh,
member, but I let it lapse. Actually, I found that I couldn't get discounts in restaurants and movies the way I thought I could with the ACM card, so I stopped carrying it.
yeah, they won't come pick you up if your car breaks down. But one of the reasons I did is because I wanted to get access to their digital library, and so I paid a little bit extra to get access to some of the journals. But oddly, the last year they open accessed basically everything, and so
Mm,
I was looking at through the journals to see, like, I'm still paying a little bit extra, and I get this sort of premium version of the journals, whatever that means. So I was poking around just to see what was there. I was looking at the sort of flagship journal, which is the JACM or the Journal of the ACM.
mm-hmm.
And on the website for the JACM, they have this thing where they show the most cited papers in the journal's history.
Mm-hmm.
And so, anyway, I had this kind of goofy thought that it would be interesting to look through and sort of talk about the most cited papers in the history of the journal.
Mm-hmm.
So the objective today is to sort of look at the 5 most cited papers in the history of the journal, which goes back to 1954, sort of on the assumption that this will give us kind of an interesting cross section of what computer science has been like over the last 70 years.
Yeah. So you sent me these 5 papers. A few of them were, well, I could kind of piece together pieces of them. I kind of got it. One of them I really liked, actually. And one of them I didn't read. I'm going to admit that right now. I didn't do the homework.
Yeah, it's hard to get through all 5 of them. And they are, there's nobody out there who's probably an expert in all 5 of these areas. I would be surprised anyway.
Are there issues with just talking about citation counts? Does that come up at all? Do you have that doubt?
I think so, and I'm using the citation counts that are provided here by the ACM itself.
Mm-hmm.
So I looked up some of these papers on Google Scholar, and they have considerably higher citation counts on Google Scholar than they do on the ACM site. And I don't know why that is. I think maybe
I think Google includes crackpot research too, right? In their citation counts?
I think they may include more journals and things like, blogs. And
Oh, wow.
I also think they may include like different versions of things. So if like somebody submitted it for a conference and then it turned into a paper, if somebody refers to the conference version, Google counts that once, and if they refer to the journal version, they count that once, and maybe the ACM does not. I don't know, but so we're kind of taking this on faith. But according to the ACM citation counts, these were the 5 most cited papers.
Well, so I would assume that the 5 most cited papers from the journal of the ACM, I would assume they're old. I would assume like pre-1990s, something like that, which actually wasn't the case. Some of these are more recent.
So it is true that a lot of them go back quite a ways, or some of them go back quite a ways. But so like if a paper is important and topical during its era, but then it's not a sort of like that research sort of falls out of favor or it gets supplanted by something else, people stop citing it. So I think one thing about these papers is that even though they go back to, I think the earliest one is 1961 or something like that.
Mm-hmm.
If you look at the citation counts, people are still citing these papers pretty regularly. I think the newest one is 2011, 2010, 2011.
Mm-hmm.
But it does seem like these papers have been pretty consistently cited, even, up into 2026.
One other little meta comment here before we start talking about the papers. My friend Aaron told me that one way to get a lot of citations is to write a survey paper. So like, here's the state of the land of this topic. And you sent me this topic and I was like, wow, Mike and I could have like, I don't know, royalty level citation numbers if we write a survey paper about the most cited papers. So that's our homework assignment for the summer.
Genius.
Yeah, just game the numbers, Mike.
Alrighty.
All right, so we're going to go. You have them in these reverse citation order, I guess. Is that how you put these out here?
Yeah, we're doing it sort of like a countdown. So, we're doing the 5th most cited first, so that it'll be exciting as we approach the most cited paper.
You won't believe these 5 most cited papers in the JCM history if it's a BuzzFeed article, starting with number 5.
So number 5 is called Direct Search Solution of Numerical and Statistical Problems. And this is from April 1961. The ACM says that it has 3,253 citations.
And when you say most cited, 3,000 doesn't sound like a lot. Now, I have to tell you, Mike, when you sent me these papers, I was like, please don't be a lot of math proofs. Please don't be a lot of math. When I got to one that had math, I was like, dang it. This one had some math in it, Mike.
Yeah, all of these are a little bit mathy,
Even the
which I guess.
hits. Yeah, okay, all right. Well, sorry. We'll wait for.
So this one was by two guys named Robert Hooke and T.A. Jeeves. And the basic idea of this paper is that they developed an optimization technique that does not require computing derivatives on the function being optimized.
So, yeah, I had to kind of reread this opening a lot. So it's like the function being. So we're trying to find a function, or we're trying to opt it. Is that what you're trying to do? You're trying to figure out the function of that produces a particular set of values.
Not exactly. So, this is basically an optimization technique. So the
Okay.
idea is you have some function and you're trying to find a minimum or a
Yeah.
maximum of that
Okay.
function.
Okay. Which that shows up
And
in chemistry a lot, right? Isn't chemistry you do that stuff a lot?
it virtually any natural science and engineering problems,
Mm-hmm.
anything that has multivariate functions is probably going to have some optimization. And
Okay. And so you think back to the
this,
math days, you got multivariate functions, and you're using derivatives often to figure out these. But in this case, these guys were like, hey, here's an idea. Let's ignore calculus. That's sort of that was the gist of my understanding in the paper. And people were like,
yeah,
those guys are onto something. Let's ignore calculus and we'll do quote unquote direct search. And this is where I really lost it. My thought was, are they just guessing? Is that what they're doing? They just guess?
yeah. So the most standard optimization techniques are going to require calculation of derivatives on the function. So the function that you're optimizing, the idea of most optimization techniques like steepest descent, or they call it steepest ascent in the paper, or things like Newton-Raphson, things like that.
Mm-hmm.
You have to have the ability to calculate first and sometimes second derivatives on the function that you are optimizing, or that you are minimizing or maximizing, as the case may be.
Mm-hmm.
And
Mm-hmm.
the reason is for that is because those tell you sort of like the directions to move in to make to find the next potential lower value point or higher value point. And so that, like you say here, their basic idea is, what if we can't do that? What if we have a function that's we don't really have a closed form for, so we can't easily take the derivative of it, or maybe it's such a complicated formula that it's difficult or time consuming to take first and second derivatives of that function.
Hmm.
Then what if we try to optimize that function, try to find a minimum or a maximum of that function just by sort of searching the values of the function.
I had this problem while reading this that it reminded me a lot, and it could be because I've been talking to LLMs a lot over the last few months. It reminded me a lot of talking to an LLM. What if we just make a guess and then refine based on that guess to a better guess? This is a very fuzzy analogy, though. Maybe not even useful.
It's sort of reflective of the technique they're using. Um, this is kind of a more constrained problem where they're trying to find a minimum or a maximum of a function. So it's not like the thing you go through with LLMs where you're trying to zero in on a correct answer by doing ask me 20 questions sort of thing.
Mm-hmm.
The basic idea is that they kind of start at some point. So they assume they can actually, they have a function of several variables. In the paper they say they have a function of k variables.
Mm-hmm.
Phi one, phi two through phi k, and they have this function which they can compute for values of phi.
But you
And
imagine
so
that this function is probably very, very large, and that's why the typical optimization techniques is not really going to be viable.
I guess large is kind of a ambiguous term there. I mean, they they do say that it's a function of several variables, so it's large in the sense that it may be like, you know, a hypersurface or something like that that you're trying to optimize in. But
I'm going to nod, but I don't know what that is. Go on.
um, so basically, what they do, as I understand it, is, you know, they pick a point at random on the surface of this function,
Mm-hmm.
and then they kind of change one variable at a time and see what happens.
Mm-hmm. That's
Like, you
roughly what
know,
I got too, which I thought is pretty funny. Why do you think
um,
this paper is cited so many times?
I think it's because this one reason is because this idea comes up a lot in real world applications. So,
Hmm.
you know, there's a lot of cases where even if you have a formula, like an equation that describes the thing that you're trying to optimize, it may just be ridiculous to try to find derivatives of that
Hmm. Hmm.
function on the fly. And
You're saying anytime
so,
I don't want to do calculus, I can be, and following the authors of direct search, we're just going to make a guess right here.
yeah, they start off with a guess essentially. So they pick a point at random, and then the way I understand it is they go through this exploratory phase where they sort of change one variable at a time, and they move both forward and backward and say, you know, does this give me a better solution? Does this give me a worse solution? And they kind of keep track of what happens for each of the individual variables in the function, and then they call this the thing they end up with after this exploratory phase they call the pattern search, I think, or the pattern move.
Hmm.
So in subsequent steps, the first thing they do is they try to make basically the same directional move that they figured out on the exploratory phase in the first move, and they, you know, the idea being that moving in the same sort of general directions is going to give them the best outcome.
Mm-hmm.
And if that doesn't work like they expect it to, they kind of back up to the exploratory phase and go through that whole process again. I think the technique has been supplanted by better things over the years, but this basic idea uh, still comes up a lot. And so this paper is cited. And I mentioned in here, I made a note in here that I saw a paper. I saw a paper from 2026 about something called quantum
Quantum
deep
deep
learning.
learning.
Yeah, there's a paper on something called quantum deep learning, which refers to this optimization method and some other similar things. So still still getting citations.
Hmm. So the number 4 paper was one of my favorites. This is the FLP paper from 1985. I was like, cool. One I know, being a little bit of a distributed systems fan, FLP, Fisher, Lynch, and Patterson. Did we do a whole? You said we did a whole episode on. I remember we talked about Nancy Lynch's work for a while.
Yeah, we did an episode which covered this in pretty significant detail. I think it was one of the two episodes we did on the CAP theorem.
Oh, okay. Yeah, that makes sense. So
So
the paper is actually called Impossibility of Distributed Consensus with One Faulty Process, 3,374 citations. If I were going to get a sweet tattoo of any of the papers, I'd probably pick this one of the top 5. Probably not the direct search one.
this is the one associated with distributed systems out of the top 5. So just as sort of like a meta comment, I do think that even though these papers may not be the 5 most important papers in the history of computer science, I think they do have a pretty good range of things. So there's like,
As a
you know,
group, as a cluster. When we write our survey paper, this is our argument. Here's your
yeah.
field.
So there's like a scientific computing one, there's a distributed system one, and we'll see as going on that there are, you know, a couple of other topics that are in different fields.
Mm-hmm, mm-hmm.
So
So if
yeah,
you want to know about FLP, maybe go back and listen to that other episode. We can do a real quick gloss on it. If you have an asynchronous network where messages can take up to infinite amount of time to arrive, you can't build a strictly deterministic algorithm protocol that'll guarantee consensus if a single process can crash. And consensus has to include those three things. All the machines agree. The answer they come to is valid, so that's validity, and that ultimately the protocol terminates at some point. It's still surprising to think about. They talk about these bivalent systems. So it's like we're deciding a 0, we're deciding a 1, and you can always get the system into such a way that it's going to be bivalent and it's going to continue to find bivalent. It's going to continue being bivalent. So it's like you can force it to not agree by just inserting the right steps at the right time. I was thinking about Nancy Lynch when we talked about her. She said later on that she found it easy to build impossibility proofs. I think about that, Mike, and I think, what would my life have been like if I found it easy to create impossibility proofs? I feel like, I don't know. I'd walk into the party and people would be like, there's the guy who proved it's impossible to build data centers on the moon right there.
Yeah, I remember that comment. I guess I associate it with like the idea that it's easier to find a counterexample than it is to prove something to be true. But
Yeah, you're probably right. It's easy to find a counterexample, but at the same time, it was just like, but this is very math oriented, And Nancy was talking about, she's like, these impossibility proofs, these mathematical proofs of impossibility are so much easier. And I was just like, what? Really? Oh, I got to take your word for it. It sounds pretty hard to me. I do have a lot of respect for FLP, though, and I can't imagine why FLP gets cited a lot. If you're writing a distributed systems paper, you're talking about consensus. There's a lot of consensus papers. There's a lot of asynchronous network papers. They're going to talk about it. They're going to cite FLP. That comes up all the time. You know what, Mike? It was interesting to read a number of distributed systems papers and then later on read more contemporary ones. And they would say, we're going to build an asynchronous network. And I could almost like skip the next lines because like, yeah, I get it. I know. I've seen this. This is not my first rodeo. Okay.
we talked about this when we covered it before, but I think everybody was kind of surprised at this result. This impossibility proof was kind of unexpected. Those are episodes 59 and 60, incidentally. So
wow, you have our episodes memorized? I don't even know how many we've done.
I actually looked it up. So
okay.
But
all right, so we'll move on from FLP. What's the next one? I think this is the one I didn't read.
Yeah, this one's probably the most mathy of them. So it's called, this is the most recent one too. So this is from June of 2011. And according to the ACM, it has 5,039 citations as of the time when I noted it. So the title of the paper is Robust Principal Component Analysis with a question mark for some reason. I don't know if that meant that they were unsure if they'd achieved that or what, but yeah, the title of the paper concludes with a question mark. And this is by Emmanuel J. Candace and Xiaodong Li from Stanford, and then Yi Ma from the University of Illinois, and John Wright from Microsoft Research of Asia.
Oh, a lot of authors on this one. PCA, Principal Component Analysis. What is it, Mike?
So principal component analysis itself has been around for a long time. It's a pretty
you've heard of before you heard about this paper.
Oh yeah. It's a very commonly used technique in data science and statistics, and the original idea goes back to the beginning of the 20th century to the well-known statistician Carl Pearson. The way that it's computed was formalized by a guy named Hoteling in the 1930s. So it's been a well-known thing for over a century now.
And what is it? Well, how do you describe it? What is
so
that?
The basic idea is that if you have a bunch of data, usually like data in a table, and you have a bunch of variables, but these variables have some correlation between them. The idea is that you can you can kind of reduce the data down to these things called principal components.
Is this okay?
And
So wait a minute. Like if you're building a linear regression and you got a lot of, I always think of that the example when I took that data science 101 class. It was like the economist at MIT is predicting the price of Bordeaux based on the weather variables, and you may have a table with a bunch of different weather variables. And he was like, I'm just using a linear regression. All I care about is rain and average temperature, something like that. Is that what you're talking about? Like you've got all these variables in a table. You care about which ones matter.
trying to think of what would be weather data. So you might have like
Humidity, temperature, average
yeah, wind
temperature,
speed, and let's say that
precipitation.
let's say that you have 20 variables like that, and then
Mm-hmm.
you have those data taken on. Well, this is going to be a bad example because I don't want to introduce time into this, but let's say that you've got that data for a particular day, but it's from 1,000 different cities in Europe or something like that.
Mm-hmm. Mm-hmm. Mm-hmm.
There's probably statisticians out there screaming at the at listening to this, but
But you know the
basically,
funny thing about the statisticians when they scream, my
yeah,
ears can't hear that frequency.
yeah, I'm too old to hear it now. So,
Sorry.
but anyway, so you've got these like 20 variables, let's say, and you've got a bunch of measurements for these 20 variables, but you suspect that these 20 variables are also somewhat correlated. And so the basic idea is that you can do this principal component analysis to sort of reduce the number of dimensions, because at the moment you've got 20 variables, and
Mm-hmm.
so to look at the entire space of those 20 variables, you're looking at 20 dimensions.
Mm-hmm.
So it's impossible to visualize for one. One thing that people will often do is sort of like an exploratory phase is they'll run principal component analysis on their data, and the one of the tricks of this is that the principal components, as you get further down, like the first principal component is usually the one that explains most of the variance in the data,
Mm-hmm.
and then the second principal component explains the variance that is left that wasn't explained by
Oh,
the
so it's
first
kind of like
principal component.
ranking. Yeah. Okay. Well, here's the most important thing for the outcome. Here's the next most
Yeah,
important thing for the outcome.
yeah. So and they're kind of I don't know if this terminology is meaningful to you, but each principal component is basically a linear combination of the variables in the overall data set. So each of them is going to be a linear combination of those 20 weather variables. So like if you want to look at clusters of data, you can take, say, the first two principal components and plot them on a 2D scatter plot. And if there are like clusters of data, they will actually show up in this principal component plot in a 2D fashion, so you can sort of see how the data is correlated.
Okay,
And
so this is a pretty well known statistical technique. But now we're talking about this paper from 2011, where they've got a new way to do it. Is that right?
yeah, so the key word in this title is robust. Robust in statistics means something slightly different than it means for us as software engineers. So
Mm.
as software engineers, we tend to think of robust as like stuff that doesn't break,
Hmm.
and robust in statistics specifically means that it's not unduly influenced by outliers.
Hmm.
So, like, there's robust versions of linear regression where if there's an outlier in your data set, it's not going to overly influence the regression line that you compete with that type of linear regression. And it's the same
Okay. Yeah.
here, where
Okay.
the idea is that if you have data which is noisy or erroneous, or just an outlier for whatever reason, it's not going to have quite so large an effect on the results of the principal component analysis.
Did you follow this paper and why? It sounds like a stats paper. It doesn't really sound like something I would associate with the Association for Computing Machinery.
Well, one, it's an algorithm. Two, it's an important technique in data science. So
Oh, okay. Okay.
it's very
And
it's
this is
very much
2011. Data science was going to be the big new thing at that. I mean, it was. People were getting paid millions of dollars to do data science.
yeah. I think that's one reason why people are excited about this. And if you read the paper, a lot of the examples that they talk about are things having to do with image recognition and things like that. So things that you
Mm.
would not necessarily like, quite a bit different than our contrived weather example. They use this technique to sort of remove shadows and extraneous noise from images.
Oh, okay. All right. All right.
Like
You're
an
selling me.
example would, this is not necessarily an application that is particularly wholesome, but one place where this could be used is in facial recognition.
Mm.
So if you like try to wear a fake mustache to disguise yourself, and defeat the facial recognition cameras, this technique can actually sort of subtract the mustache and reconstruct what your face would look like underneath the mustache.
Oh, because that
So,
mustache is an outlier. And we want a robust reconstruction of your face
yeah.
statistically.
So yeah, it's hard to describe the method that they use in here. The normal principal component analysis algorithm is actually pretty interesting because it uses something called singular value decomposition usually, which is probably one of the most important algorithms of the like applied mathematics world.
Hmm.
Um, but this one, as I understand it, they use a different optimization technique, but they somehow managed to devise this algorithm that finds the principal components in a tractable way. So I think it was a little bit of a, I think the fact that this worked was a little bit of a surprise to people and had a lot of applications, which is why it's so frequently cited.
It's, I mean, the pursuit, what we're trying to get at here sounds really useful, but you didn't really sell me on I should read the paper. I still feel like I'm going to be completely lost trying to read this paper. There's no way I'm going to read this paper.
Yeah, it's a very long paper for one. I believe it's 37 pages,
Mm.
and a pretty considerable amount of it is mathematical proofs. So
Oof.
it's
Yeah, not my kind of cup of tea there. Although
not
I'm okay with if a paper's 37 pages and the appendix is 29 pages, that's totally fine because you don't have to read the appendix, is what I've learned.
yeah, this one this is not one of those papers where they cram all the hard stuff into the appendices. This,
Do you think they
unfortunately,
do that for people like me to hold my attention?
I've heard this from friends that I have in academic world that one reason why people use appendices is because a lot of times these papers initially get published in conference proceedings,
Mm-hmm. Oh, and it's got to
and
be shorter for the
it's
conference,
got to
right?
be shorter. Yeah. So
Yeah.
anyway, yeah, it's a it's a very interesting result, and if you if you have a strong linear algebra background or a strong background in optimizers, it's probably readable for you. But
Hmm.
for everybody else, I would suggest just take our word for it.
Take Mike's word for it. You can take my word for it. So we've had direct search was the first one, which I kind of like the underlying message there. Maybe I'm taking the moral of the story I got was you don't need calculus. And then the second one was FLP. And the third one here is principal component analysis. Sounds pretty cool. The one that I liked is the next one. I mean, I love FLP, of course, but I've already read it. This one's called Authoritative Sources in a Hyperlinked Environment. It's a page rank type of algorithm they're describing. Like, how do we run a query on what's the most relevant set of websites in response to a user search? I thought that was cool, but it came up a little later than I would have thought. September 1999. Google was pretty well established at that time, and it's pretty different from PageRank.
Yeah, I mean, it has some superficial similarities to PageRank. The author of this paper, yeah, John Kleinberg, and
From Cornell.
yeah, I think he's at Cornell now. I'm not sure where he was at the time.
I thought he was at IBM when he worked on this. I thought it was part of some IBM research. Well, let me read to you something from the paper that I was like, huh. So here's a check from the paper. In particular, consider that current search engines. Now, friends, we're in 1999, okay? So take a trip back to the 90s. Current search engines typically index a sizable portion of the www. Oh, and sidebar, I thought it was pretty quaint how they kept talking about the www in this paper. It's like, when I talk about just the internet in general, they just keep referring to the www. Well, that's cute. I really like that. Anyway, current search index typically index a sizable portion of the www and respond on the order of seconds. Although there would be considerable utility in a search tool with a longer response time, provided that the results were of significantly greater value to a user, it has typically been very hard to say what such a search tool should be computing with this extra time. And this leaped out and punched me in the face because I was like, huh, you think there's a lot of utility in a longer response time? Are you serious? So we were using
Well,
Google at this time, and they'd be like, here's 4 million results, and it took us 2.3 seconds to come up with that. And Google was definitely, they had pretty much won by 1999.
yeah, I mean, the subordinate clause there, the provided that the results were of significantly greater value, I suppose is true. You know, you might be willing to wait a second or two longer if the results were better. But I believe by 1999, Google was pretty well established. I'm trying to remember when I stopped using Alta Vista entirely and
It would have been like
switched over.
96, 97 for me.
Yeah,
We started using
pretty
Google pretty
sure.
active at like 98, I could tell.
Yeah, I think by this time most people I knew were using Google. But
Mm-hmm.
yeah, it has this sort of superficial similarity to PageRank in that it has to do with, you know, the number of links pointing to a thing, or the there's sort of this like recursive thing of like you know, a page which points to a lot of authoritative sources
Mm-hmm.
is
Mm-hmm.
interesting, and a page
Yeah,
which is pointed to by authoritative sources is interesting. And so,
Yeah, I thought they had some stuff in this paper that I thought was like philosophically interesting, and I think it just provided me with the most questions as I was reading it. They do this distinction between quote authorities and hubs often point to authorities, and authorities are pages that have authoritative information about some topic. And they're like, you could dynamically query these on the spot when somebody's submitting a request. So they to say, so imagine you've got a page and there's all these links that are navigation. Those are internal to the whatever that website. We're going to kind of ignore all those. And we're going to look at the base query of like the space of information, and we're going to see who's everybody pointing to and what are those pointers, those authorities back pointing at also. Here's a line from the paper. In this work, we propose a link-based model for the conferral of authority and show how it leads to a method that consistently identifies relevant, authoritative www pages for broad search topics. Our model is based on the relationship that exists between the authorities for a topic and those pages that link to many related authorities. We refer to this pages of the latter type as hubs. And we observe that a certain natural equilibrium exists between hubs and authorities. As I talk about, they're building this graph. So we exploit this to develop an algorithm that identifies both types of pages simultaneously. So you've got hubs and authorities. Well, I found this really like a provocative idea.
the sort of difference between this and PageRank is that, you know, PageRank is kind of set up as this like random walk through the internet, and
Mm-hmm.
so it's similar in the sense that things which get more links are more interesting.
Mm-hmm.
If, you know, things that for a particular search term, things that get more links are more interesting. But
Mm-hmm.
it has this sort of duality of one thing being this hits has this duality of one thing being an authority and one thing being a hub, which seems different than PageRank.
Well, and PageRank 2 is totally offline. Like, I mean, they build this giant cache and they or data set, they cache it, and when you submit a request, they look in their cache for the answers, And the authors of this paper are like, no, we're going to do this on the fly. We're gonna analyze a set of results. They talk about this mutually reinforcing thing. They say the hubs and authorities exhibit what could be called a mutually reinforcing relationship. A good hub is a page that points to many good authorities. A good authority is a page that's pointed to many good hubs. There's almost a chicken and the egg thing, though, right? Because I needed to identify the first good hub or the first good authority before I could say, like these are good, quote unquote.
It's kind of a self-consistency thing too. So it's like you can't you can't immediately uh, identify a hub because a hub is defined in terms of the authority of things that it links to, and so you have to figure out the authority of those things
Mm-hmm.
before. I didn't really catch
The score.
how they initially assign authority.
Yeah, so I think they have these two scores, authority score and hub score, right? And they start equal, and then there's a bunch of linear algebra, and they start talking about eigenvalues, eigenvectors, eigenspaces, and I was like, okay, you guys are losing me. But somehow they use linear algebra to compute the authority score and the hub score, and that also sounded like I started thinking about LLMs again. Mike, sorry, I guess I should not be thinking about LLMs with everything. We're reading the past so that we don't have to think about LLMs for a while. It's like when it gets real hot outside, you go to the movie theater. That's what I'm trying to do here.
Exactly. Yeah.
Here's another section from the paper. There's a cyclical reinforcement, they say, and it mirrors, quote, semantic relevance, how meaning and authority strengthen each other contextually. Now, I read a sentence like that, it just sort of tickles my brain in a, do they? I can't, I can't help but just sort of wandering around puzzling over this. They write, and I bolded this, in a semantic context network, your hub pages, they're like they connect to your authority pages, and that reinforces the hub's like credibility. So this is a tool that's trying to figure out where's the expertise. And maybe it's a shallow distinction, but Google's page rank is more about what's relevant, what's the most relevant. And these guys are like, what's the most authoritative answer? And I like that. That's cool. That's an interesting pursuit. But I also feel like we now have an internet that's filled up with bullshit. So, like, what does authority mean in the face of disinformation and misinformation and just total bullshit? It almost feels idealistic a little bit.
Just as an aside, page rank is also basically a giant eigenvalue problem as well. So
Oh, I didn't know that.
um, yeah, it's conceptually explained as like this random walk from site to site, but the way it's actually computed is this massive eigenvalue problem.
Hmm.
But so I thought this paper was interesting, and there seems to be quite a few like relatively recent uh, references to it. So people are still thinking about this and looking for applications of it.
Well,
But
I think the LLM, that seems like a pretty clear one, right? Like, because you're trying to find what's the most likely authoritative text that would match this.
so I think you've already said this, but this method never really got used in a search engine like
They built a
PageRank did.
prototype for it. I looked this up, and they built like an IBM prototype, but yeah, they didn't. By then, Google had already won,
Yeah, and
and it was like, oh, it turns out people don't want a slower one.
I think part of it was that it had to do this computation on the fly, whereas Google was building all this stuff offline from crawlers and data
Mm-hmm.
they got from crawlers, and so it just wasn't performing well enough. But also, so there was no search engine built around this, and also it seems like this stuff that you mentioned about semantic relevance and semantic context network seems like it probably has been supplanted by deep learning stuff.
Hmm. I just would
So
have thought that it goes into the deep learning stuff. No, it doesn't. There's no obvious like deep learning comes out of this.
yeah, I mean, we found this one reference where it says that there's a paper called hit space propagation paradigm for graph neural networks. So this idea is apparently still used in a number of places, and one thing that it's used for is graph neural networks. Yeah, I guess so. What I was getting at is that I'm actually kind of surprised that this paper was cited so many times and
Yeah.
continues to be cited.
Yeah.
It's been cited, according to ACM, it's been cited 6,132 times, and it was published in 1999. So it's the second newest paper on this list, but it's also the second highest number of citations.
Well, there's one other surprising thing I wanted to raise here. They write they're saying we're going to build up this graph of expertise, but we're not actually going to read the content of the pages that we return to you. They say the point we wish to make here is not that text is best ignored in searching for authoritative pages. However, the results above show that a considerable amount can be accomplished through essentially, quote, a pure analysis of link structure. That strikes me as kind of counterintuitive. Like, we're not actually going to read the things. We're just looking at the links. And from those, we could somehow figure out what's a good authority and what's a good hub. And then if you could do that just by building a graph with links, you could look at any graph and say, what's the most authoritative section of this graph? You could look at a social network. They even talk in this paper about, quote, bibliometrics, right? The study of written
Yeah.
documents and how they cite things, like citing scientific papers and what makes them important and stuff. Like, that's another application to this.
Yeah, I read something about how this is sometimes applied to what's the concept called? It's the thing where they sort of rank the importance of
That
scientific
citation.
papers.
Yeah, exactly. Yeah, that citation score thing. I think they almost
Yeah.
even talk about that here, right?
I mean, I'm not quite sure what they're saying there. Like, are they saying we can even ignore the search terms? It doesn't really matter.
No, I didn't think that, because they're like, we're just pure links. And my takeaway from that was, we will look at the content of the links, like an anchor, like an href. Here's the link. Here's the actual textual content. And that's all that matters. And so somehow that forms like a graph edge. And everything else on the page, we're going to ignore. Doesn't that seem like super gamifiable, though? I mean, it was surprising to me that this produces good results, albeit slow.
Yeah. I guess, long story short, I think there's probably some subtleties here that I'm not understanding, because I don't think I understand why this is still such a popular topic.
Well, I think it's because of linear algebra. Linear algebra is always a hit, Mike. People love it. People love linear algebra.
Yeah, that's true. I sometimes, think, well, I'm not really interested in this, but it does have linear algebra. So
That's how we decide what to watch on Netflix, actually. No, that doesn't look good. Oh, that has some linear algebra. Put that one on.
that's actually not as outlandish as it sounds.
It's
Because,
not?
yeah, because way back when I was working in recommendation stuff, do you remember the Netflix contest?
Vaguely, yeah.
We should do an episode about that. So back in like 2006 or 2007, Netflix did this. So this was kind of like the early days of recommendations, where
Right. Based on what you've
Amazon
watched, we think you would like to watch these other things
yeah,
that these other people liked. There's a sort
yeah,
of nearest neighbor overlap, you and these other people.
right. And so Netflix, they started this contest, and the basic idea was, here's a bunch of data about movies that people have watched. We'll give you $1 million if you can find a better way to do this. And
That's
so,
right. I forgot about that part. Yeah, that's right.
so there was like this $1 million contest to see who could come up with the best way to make recommendations based on the Netflix data. Anyway, to get back to the point, the method which eventually won and became kind of a basis of a lot of recommender systems going forward from there was based on the thing that I mentioned earlier called singular value decomposition. So linear algebra, man, I'm telling you.
So if we got really good at linear algebra, we could just go out and win these $1 million contests with it.
Yeah. I mean, I suppose you have to know neural networks now too.
Oh.
But
It's kind of like going into a football school in Europe, signing a contract, or getting drafted to play baseball, learning linear algebra. That's your ticket.
yeah, I guess neural networks are mostly linear algebra too, so that helps.
Okay. So paper number one. This one,
Should we
I
have a drum roll?
this well, I think it's gonna be anticlimactic. A drum roll. I mean, I don't think I finished it. I think I kind of smuttled through pieces of this. Parts of it made sense. Parts of it I had to squint real hard at.
Did this surprise you?
That it's the
This,
number one.
yeah.
So this one's about scheduling, and yes and no. Like when I see these well-cited papers, FLP immediately, oh, okay, that makes sense. The PageRank, the hits algorithm, I was like, I do not get why this is so widely cited. The direct search one, because I've never used it or heard of it. I could sort of, you could tell me, oh yeah, that gets used all the time. Oh, okay, I believe you. This one, you could say to me, yeah, this is the foundational paper on which all scheduling systems for all CPUs following the mid 70s were, implemented based on these principles. And 100% I would believe that.
So the paper number one is called "Scheduling Algorithms for Multiprogramming in a Hard Real-Time Environment," and this is from January 1973 and has 7,218 citations according to the ACM.
Can we just unpack the title a little bit? So scheduling algorithms. All right. So we've got different functions and user space that we want to run. Multi-programming means different programs, right? Programs that may overlap in what they want to do. They need to finish in some time, but why hard real time? What do you think that it really means?
So I think there's two terms here which need a little bit of clarification for me anyway. One is multi-programming. So I don't think people use this term as much anymore as they did in 1973. I think people might say multitasking now. I'm not sure. But basically the idea is you have a single CPU. So there's not like multiple processors. There's not like cores. There's just a single CPU.
Mm-hmm.
And you need to run multiple programs on that CPU effectively, not simultaneously, obviously, but
you need to schedule them. You need to overlay
you need to
pieces
sort
of
of
them.
interleave them, so
Yeah.
they can both run.
Yeah, which we're completely used to. We deal with all the time anyway now.
Yeah, so that's what multi-programming means here. And then the other term is hard real time, and this is
That
something
term I stumbled on.
Yeah, I didn't really know what it meant, to be perfectly honest, because I've never done real time. I've never done hard real time stuff. The basic idea is in a hard real time environment, a task has to complete. So I'm going to read this thing to see if it makes sense, because I think this is from the paper? Yeah. Process control computer performs one or more control and monitoring functions. The pointing of an antenna to track a spacecraft in its orbit is one example of such functions. Each function to be performed has associated with a set of one or more tasks. Some of these tasks are executed in response to events in the equipment controlled or monitored by the computer. The remainder are executed in response to events in other tasks. None of the tasks may be executed before the event which requested occurs. And then here's the important part. Each of the tasks must be completed before some fixed time has elapsed following the request for it. If that doesn't happen, then there's a failure.
Yeah. So we need this program to finish by this time, or this particular task to finish by this time, and it's considered a failure if the task does not finish in that time.
Right, and so they were trying to develop scheduling techniques that would essentially guarantee that all the tasks would complete, so that the systems that they were interested in, which were things like airplanes and tracking systems and so forth,
Mm-hmm.
would not fail in catastrophic ways.
Mm-hmm. Mm-hmm. Yeah, that makes sense. I was thinking about like the Mars rover, right? You're going to put some operating system onto a Mars rover, and apparently this paper was involved in stuff that got used in Mars rovers. And you're going to ship that thing to Mars, and you're going to want it to beep around, and every single little thing it has to do, you have to guarantee that process finishes in some satisfactory amount of time in order to be assured that that little rover is going to keep going.
Yeah, and I guess you could sort of contrast it with soft real time, which would be something like streaming video or something where if the task gets stalled, it's not the end of your life.
Mm. So everything gets a priority. That was the part I followed. So we have deadlines, different deadlines, maybe for different programs, maybe for different tasks and programs. And they talk about how you can have a fixed priority or a dynamic priority where the priority changes based on what's coming up next. And they have a fixed priority proof and a dynamic priority proof. And I had to do a lot of reading, meta reading on this paper to kind of understand. But the fixed priority proof, they call it rate monotonic scheduling. This one seems pretty easy because they're just like, just do all the ones that are the shortest. You just sort of like, you stack up all the shortest ones with the shortest deadlines, you do those first. And as long as you don't have a number of tasks that go beyond some total percentage of the CPU, then it's a guarantee that they'll complete. And I have this mathematical proof in there that there's a guaranteed completion.
Yeah, it's something like 69.3% or
Yeah,
something like that.
yeah, that sounds right. Yeah. Don't come back, Mars rover, until the mission is over. And if I know, I have fixed priority for all of your tasks. You gotta pick up the dirt and put it in your little dirt tray. I can guarantee that these tasks complete in some period of time. We're going to lose the sun. You're not going to be able to get power for that time, Mars rover. You have to go to sleep. Maybe I'm going too far into the Mars rover metaphor here.
But like the idea, I guess, is that you've got something that has to monitor, and then you've got something that has to control. And
Mm-hmm.
if the monitor task doesn't finish when it's supposed to, and the control task gets, if the thing that's controlling your wings or something doesn't get to run, and you might crash into the side of a mountain.
Yeah, right. That makes sense. Right. Yeah. And so they talk about how scheduling is really about assigning priority. I kind of jumped over that. I meant to say that first. I figured that would make sense to you because of the stuff you've looked at before with the completely fair scheduler. Is that how you think of a scheduler? Just assigning priority to tasks and then running the highest priorities, running them in priority order?
Well, there is a certain, I think it's been replaced now, but the fair scheduler in Linux was kind of like that, where you were essentially pulling tasks from a priority queue.
Mm-hmm.
The priority queue was built as a red-black tree, but the idea of priority might be a little bit different when you're running Linux as opposed to running
a spaceship. They do say, that in their model, the algorithms they're looking at are preemptive. So whenever there's a request for a task, this is from the paper, that is of a higher priority than the one currently being executed, the running task is immediately interrupted and the newly requested task is started. Now that surprised me because what they're ultimately saying is if you use this for fixed priority, we can guarantee it will complete without failure in the time. And I was like, really? Even if you just arbitrarily interrupt with the high priority, like that's sort of surprised me.
I think the other method they came up with is something called earliest deadline first, which
oh yeah, that's right, or deadline driven scheduling. Earliest deadline, yeah, I think you're right, that's what they called it.
yeah,
So these are for dynamic priority. So there's the fixed priority is rate monotonic, where you just take all the ones that are shortest, and then the other one for dynamic priority is deadline. I have it as deadline driven scheduling.
Yeah, the way I've heard it described is earliest deadline first.
Okay, that makes sense because here's what they say: a task will be assigned the highest priority if the deadline of its current request is the nearest, and will be assigned the lowest priority if the deadline of its current request is furthest. So you're kind of like shuffling them around. Oh, your turn.
I think there is or was a version of this type of scheduling in Linux at one point, what they call deadline scheduling.
So they have these mathematical proofs in here, and the mathematical proofs are like, look, if you add up all of your tasks and all of your deadlines, as long as in the fixed sense they don't go beyond 69%, and in the dynamic sense they don't go beyond 100%, boom, you're good. Just ship it. I was like, what? Really? And then I think I can sort of imagine this paper being cited so many times by people who are shipping satellites or airplane software or Mars rovers. And like, yeah, we know this works because following the authors of deadline scheduling algorithms for multi-programming hard real-time environment, we know that our tasks do not exceed this percentage of the CPU. Boom, we're done. Boom.
It's important to note that people were doing this before 1973. This paper was published in 1973, but by then we'd already put people on the moon. So it's not like this was the beginning of real time systems. It's just that these guys put together like a mathematical framework that sort of would guarantee that these things would work. And before that, they had to like extensively simulate the things
Yeah.
that they were
Yeah.
building to make sure that they
That's a
were.
really good point. Yeah.
Um,
So
did
yeah,
we say?
before that you would have to have like heuristics, like, hey, I think this will work. Let's just not exceed. We'll just be super conservative, or we just simply won't do multi-programming. We're going to put somebody on the moon. We're going to do one program at a time. But how do you do one program at a time if it's like, well, I need the oxygen system and the system that checks whether we could still take off to be functioning all the time? Like, I want both of those to work, Mike.
Yeah, I think they just. I think in the early systems they did two things. One was lots of testing and simulation, and the other thing was lots of redundancy. So they were
Mm.
pretty
Mm.
pretty substantially over engineered. But
Hmm.
did we mention the authors of this paper? I can't
No,
remember.
no, we didn't, and I actually
Okay.
forgot. I forgot to include that in my notes here. I just was mostly like, I'm kind of following. This is surprising. I find this a surprising result.
So it was written by C.L. Liu and James Leyland. The first one who was at MIT, and Leyland was at Caltech. So
JPL, yeah,
JPL, yeah,
yeah.
which makes sense, I guess.
Well, I was like, where did they use this? And that's why I kept talking about the Mars rover because I had heard that they would use it and they had been used in things like that. It's maybe been used in some of modern processors. That's like underpinning the way in which modern processors are designed, and also in cars because you've got shared resources for like I've got my I don't know my braking system and my collision detection. Like my wife's car has this eyesight thing with these cameras, and you want to make sure that that's working. But oh, I also need to be able to touch the Spotify button.
Yeah, I mean, I think these things have been improved upon in the last 50 years, but yeah, I think I looked at some of the recent references, and this paper is still quite frequently referenced and cited in books and papers. So
I kind of thought there'd be more. So these are the top five. We've got the multi-programming. I could kind of buy that. We've got the hits algorithm. That one's the most surprising to me that it's cited so widely. Robust principal component analysis, no comment. FLP and direct search. Direct search, again, you just sort of, I'm easily convinced that that's widely cited. FLP, oh yeah, I buy that, yeah. Was there anything in the list where you were like, wow, I would have thought there'd be more, I don't know, graph algorithms? Is this ultimately telling us, Mike, that graph algorithms are not real? I mean, they're used in these papers, but like, I don't know. The B plus tree paper is not widely. Oh, it's not from the ACM, I guess, right? Because this is ACM only.
there are certain things that I was surprised were not in here, and I think part of it is a lot of the most interesting things were in more specialty journals. So this is again the
Okay,
main
yeah.
journal of the ACM. So
Yeah. Like
like
Lamport's clocks wouldn't have been published in the Journal of the ACM.
yeah, I don't think Lamport's clocks was here, but things like the papers on deep learning and the transformer paper and stuff were in either like more esoteric topic specific journals, or like I thought there would be at least one paper in here on computational complexity.
Yeah.
Um, but again, I think that might be something that comes up in a more theory oriented journal.
Hmm.
So
What about paper like large citations for papers across all of computer science? Is that a harder type of aggregation to figure out?
probably not. Probably a Google Scholar thing if you're willing to do the research. I considered doing that, but I figured this was probably a good place to start.
Yeah, and this is an interesting place to start. It's a little surprising that some of these, but all these papers have surprising knowledge in them, for me at least. It's fun to think about. Oh, here's 1961. They're working on this problem. Oh, here's 1973. I thought about Brian Kernighan's book. They're working on Unix over there at Bell Labs, and here's this multi-programming paper.
I also considered talking about the least cited papers, but that's harder to choose from because there are quite a few. There are quite a few papers that have never been cited, sadly.
I would be up for that, Mike, if we go and talk about like the cranks, the weirdos, the total kooks. I find some interesting stuff reading it because I don't consider myself someone who's really savvy. So I read the crank paper and I'm like, wait a minute, is this top fool? Is this just BS? Is this metaphysical weirdness going on here? Who can tell me?
There's not a lot of that in this journal, but there's some stuff from the early days where it's like, we're going to talk about the analog computer that we use at MIT for flight simulation, or we're going to talk about this thing we did with where we used a magnetic drum for a disk drive, or we're going to talk about using paper tape to process insurance forms or whatever. It was probably super interesting in 1954, but
I think what you're telling me is if you want to write a paper that does not get cited, write a paper using a technology that is just becoming obsolete, and it probably will never be cited.
Yeah, like you could write a paper on floppy disks.
Yeah, or Betamax or something. Who's going to publish that paper? Oh, sorry, editor. All right, Mike, I have a homework assignment for you. Start our paper that is a survey on the top cited papers, and I will edit it with you. I'm asking you to write it, and I'll be second author.
Do you think we can get an LLM to write it?
Oh, yeah, probably, but then we would be disgusted with ourselves. Hey, what would our associations be on that? It would be Mike Mull, Picture Me Coding, Eric Aker, Picture Me Coding. That would be our association for that.
Yeah, we could do that. Yeah.
Could you just independent scholar / Picture Me Coding?
We could be the first people to write a paper as representatives of a podcast.
Oh, I bet that exists. I bet that maybe if we could be the first. All right, Mike, I think this was an interesting topic. I'm going to think about this hits paper. I'm kind of walk around thinking about it because there's a little bit of philosophically interesting stuff in there, like what's authoritative? What does it mean to be authoritative? Is it valid to just talk about what points at what else to figure out what's authoritative? Like that's not an easy question.
I'm going to think about principal components.
Oh, yeah. Yeah. Make some money, Mike. Get the dollars. Well, this has been Picture Me Coding with Eric Aker and Mike Mull. Thanks for joining us. We'll see you again in a couple weeks, although I might be on vacation. We might miss an update here, friends. So if you don't see us for a month, that's me out of town. But go to see Mike, DataCon, LA, August 22nd.
Yeah. Long Beach, August 22nd.
And use the code MULL, MULL 25 to get a discount to go to DataCon LA. And we will see you again sometime in 2026.
See you next time.
Bye.